Okay, thank you very much, Fredrik. So, and it's great to be here. Thanks a lot for the invitation. So, I have to use this one. So, yeah, the topic of my talk is a partition function of planar Coulomb gases. There are many versions of this, so I will not put this into a great sort of tell you or sort of make a survey of this. So I just mention some things. So what we have is the important part is that we have particles in the complex plane. So think of these as positions of particles in the complex plane, and they interact with this logarithmic energy here. So this would be the total energy, interaction energy between the particles, and beta is a parameter, the inverse temperature as usual. And then we have some reference measure. I mean, if I didn't, this of course is not integrable, right? So I have to have some more things in order to make this convergent. This is something I may or may not have. This is sort of sampling with the so-called linear statistics, the points, right? So I take some function and I sum over all points. It's called a linear statistics. So there are different possibilities here. I could sort of, this reference measure could have this form, right? Where I sort of have some confining potential, I mean, which would keep the particles in a finite part of the plane in the limit as n grows. So we're interested in the limit as n goes to infinity, right? So this is a much studied class of models. It includes various random matrix ensembles. I could, for example, restrict this to the real line also. Then it would include, say, things like Gaussian unitary ensemble or Gaussian orthogonal ensemble. And Cj would then be the eigenvalues, right? And also normal random matrix ensembles fit into this. This is a big area. I will not talk about that at all. Another possibility is to sort of confining these charges by forcing them to be in a certain region. So I could say they all have to be inside the unit circle or some other domain. Right? Or what will be the focus today, I could say that they have to be on a rectifiable curve. And the reference measure then is just the arc length measure on this curve. So a classic, basic example there, you should think of a unit circle. And you could take, say, beta, the parameter there, beta equal to 2, and then you would have what's called a circular unitary ensemble or Haar measure on unitary matrices, and the points will be the eigenvalues. So this is the type of ensemble I will be talking about today. So it could be a closed curve. I will come back to that a bit later. So a bit more detailed notation, I would write this like this. So I included this psi indicated, this a part of it. Of course, you can think this is sort of a weight of a probability measure on this curve. And if I want to take expectations with respect to this probability measure of sort of linear, this kind of Laplace transform of linear statistics, it's sort of a quotient of these two partition functions, yeah, just by ordinary definition, right? So in particular, what I will be interested in today is the case when the particles are confined to a Jordan arc like this. We can sort of scale, so it's always between -1 and 1. I mean, fine transformations won't really change anything here, right? And I will also concentrate on beta equal to 2. This is not necessary. We can treat general beta. And as mentioned on the first slide, this is joint work with Fredrik here and also my former student, Klara, Courteaut. And we do treat general beta, but just for simplicity, let me stay now with beta equal to 2. So then we have this kind of object, right? So I put beta equal to 2. We have the interaction. We have this linear statistics. And what can we say about the asymptotics of this object? So please interrupt if there are any questions and unclear points. So for beta equal to 2, it's a fact that this object is also a determinant. This doesn't really play a role in the proofs or anything, but just to connect with other results. So if I go back here, if you look at this part and sort of cancel the minus sign, this is, and take the exponential of the log, this is just a product like this, which you may recognize as a Vandermonde determinant. So you have this fundamental determinant squared, and then by linear algebra manipulations, this whole integral actually you can sort of take is a determinant where the integral is now inside the determinant instead. And a particular case, which is sort of the reference case in a way here, is when the interval is just the unit, or not the unit, by the interval from -1 to 1. So then this integral would just be the integral from -1 to 1 of xj plus k minus 2, and then you have this weight here. This is a very classical object. It's a Hankel determinant because it only depends on the sum of the indices here. And asymptotics of this kind of object is an old story going back to the 60s. So in this case, many things are known how this behaves, right, by older theory. Right? So this is sort of a basic case, and different random matrix ensembles also fall into this type of object. So, and a basic result there, which we will actually sort of use in a sense, is not directly by applying it, but by you get similar computations here, is that we have sort of a strong Seger type theorem for Hankel determinants. So this was, as I mentioned, studied in the 60s. So if you take this sort of function that we had in the linear statistics, this is sort of the equilibrium measure of the interval from -1 to 1, and you assume that this integral is equal to 0. Then you can expand a function in Chebyshev polynomials, or if you wish, you substitute t there in the interval for cosine, and then it's a cosine series. So this condition is that there is no a0 term in this series, right? So you can expand this function, we assume that it's sufficiently nice. Then this theorem tells us that this object, the expectation of this linear Laplace transform of this, which is this quotient here, then has a limit as n goes to infinity. And this limit involves this a of psi here, which you can write in terms of these coefficients like this. This is often the form you would see in this old literature that I mentioned from the 60s and so on. And if you've seen the Seger theorem on the circle, you would recognize this type of expression. It can also be written, and let us note this, in this form as a Dirichlet integral. So you take the bounded harmonic extension of this function on the interval into the whole complex plane, and you compute its Dirichlet integral like this. Then these two objects are the same, and we will see that this is a kind of form of this which actually generalizes very nicely. And you can also see there is an interpretation of this also, if you think of these. So we have these points here, right? C1, C2, Cn, and these are sort of random points under this measure, and we sample them like this. So what this theorem tells you is that this actually converges to a normal distribution with a certain variance, which is essentially this a of psi there. So what this result, Seger theorem, tells you is that linear statistics like these are normally distributed in the limit. And you have this formula also for the variance. Right? So in this, I mean, this was, let me go back. No, it doesn't. Well, yeah, no, yeah. So
Gaussian free field behavior or some?
Yeah, this is a kind of a Gaussian free field restricted to the sort of to the arc, yes. So here we have the quotient, right, of these partition functions, which gives us the expectation. I sort of normalized by the partition function, the probability measure. We can also look at the asymptotics of this object itself, which is not really, it's not completely trivial to compute this normalization here that we use. And it has a formula like this, going back to Widom. You can compute using orthogonal polynomials, or it's also a so-called Selberg integral, if you know what that is. And you can compute it asymptotically. It has this 2 to the minus n squared is actually the capacity of this interval to the power n squared. You will see why in a moment. There are also the other terms depending on n. This 2 pi n is not really interesting, and there are some other objects here. So, what we want to do now is sort of deform the interval, right, to some other curve and see what happens under this deformation. How does the partition function somehow depend on the curve, right? And then it's natural to look at the quotient here, because you don't really want to try to understand this behavior as part of understanding the behavior of this Jordan R, right? So we look at this quotient, and so what happens with this? I mean, as n goes to infinity. So the first thing, you have to see what's the leading behavior here. And if you sort of think of if we go back and here, you see, I mean, you could expect that these particles repel each other strongly. So they will follow in the limits more or less some continuum distribution, right? And this would be sort of minimizing this thing here, right? Which is, if you know things from potential theory, this would mean that this should somehow converge to the equilibrium energy of this Jordan arc. And this is indeed, as you can prove, it's a dominant behavior. So there will be a limiting sort of distribution of these particles, which is the equilibrium distribution of this curve, which is the same thing as harmonic measure from infinity. And this energy here is what's sort of the definition of the logarithmic capacity of this curve. So capacity to the power n squared is sort of the dominant behavior. This is what we saw in this special case. The capacity of the interval is a half, and we had 1/2 to the n squared as part of that asymptotics, right? So this is not really interesting. It doesn't tell you anything about the geometry of the curve, because you can just scale things, right? So we divide this away here. This 2 here is just sort of for convenience. It's not really so important. But we have divided away capacity to the n squared. And then we get this normalized partition function. And so the theorem that we prove is that we assume that this curve is very nice. It's an analytic Jordan arc between these 2 points. And then we have a limit of this quotient. I take the logarithm of this kind of free energy, and n goes to infinity. There is a limit, which I denote in this way. And what I will do in the talk today is to try and describe what this limit is. I mean, I'm just saying there is a limit. There is a finite quantity here, which I called JA here, of gamma. So, but what is this? So how would you compute this, actually? I mean, we have to somehow, there's a limit, right? We have to compute the limit. So how would you actually do that? So you could imagine doing it this way, so this is the integral, this multidimensional integral we want to compute. We integrate over all points over the curve, right? We have the arc length measure. So somehow, how do we describe the curve? Well, we could parameterize it, right? We parameterize the curve. It's natural to parameterize it with the interval, right? So we have the interval -1 to 1, and we have some parameterization of the curve by the interval, right? So let's call this C of t like this, right? So then I just change this. I will get a contribution, of course, from the arc length measure here. So I get this integral now, but now I'm integrating on the interval instead, right? So if we were just on the interval, then we would have this expression, right? So say this is the identity, all this just becomes this. I sort of we wanted to compare what we have if we just have the interval, right? So what's changed compared to just having the interval? Well, you have this part, right? You just sort of add and subtract this quantity. Then you get this object here, where I equal to j corresponds exactly to this thing there, right? So this sort of captures everything about the curve now. Right? But so parameterization should we choose? I mean, in principle, we can take any parameterization and try to understand the asymptotics of this, right? So it turns out that there is sort of a one convenient choice from certain sort of computational aspects here now. So that's the next question. What parameterization should we actually take here? Right? Is there a good parameterization from the point of view of computing the asymptotics here? Well, somehow, as I said, the points sort of distribute. There is sort of an equilibrium distribution here, and there is an equilibrium distribution here, right? Somehow, if I just take any map here, the equilibrium distributions won't really match, right? I mean, so I would move the equilibrium distribution here to some distribution of points here, right? What I want to do is that I want to move from the equilibrium distribution here to the equilibrium distribution there, which would mean somehow that I follow what I should have if I just had was on the interval somehow. So this is the idea of this equilibrium parameterization, right? So I map T to CE of T here, where the sort of measure from -1 to that point, this part here with the equilibrium measure is the same as I would have on the interval. So I map sort of the equilibrium measures to each other in this way. Then we have this kind of expressions, right? This is the kind of object, that we want to understand, the log of a quotient like this. Right? So what I do is that I expand this in a series in terms of the Chebyshev polynomials here. And it's not obvious why you should choose the Chebyshev polynomial. So you can sort of suspect it when you saw they occurred in this asymptotic we had for the Hankel determinant when it had -1 to 1, right? So I'm claiming that there is an expansion like this, which we call sort of an arc-Grunsky expansion. It's sort of an analog of the Grunsky expansion, which I will come to later in the case of a closed curve. Right? Note there is an important fact which this is sort of where the capacity comes in as just a scalar, but this summation starts not at 0 here. So, I mean, if you just expand this function in two variables in Chebyshev polynomials, this sum would start at 0. But it doesn't here, and the reason is exactly because this is the equilibrium parameterization. You use the variational characterization of the equilibrium measure to see that you don't have any k equal to 0 terms here. So actually have this type of expansion, and assuming sufficient regularity, which we certainly do now, since we assume it's an analytic curve. Right? So I rescale things a bit here. I sort of put on 1 over square root of k, 1 over square root of L as normalizations in front of the Chebyshev polynomials here. This is a great analogy of what you do for the case of a closed curve, which you will see later. So then we define these bk, just these products, right? Because we sort of have to compensate for these, right? This gives us an infinite matrix now, acting on little L2 space, right? And this is this operator, which we call the arc-Grunsky operator then. So let's sort of insert these things into the formulas we had, right? We have this expansion now, right? And we use it. This was the thing we had, right? This is the logarithmic interaction just on the interval I. This was the effect of the curve, right? So I now want to expand this using this formula here, right? So I introduce Ti, Tj, right, and sum over everything. This will mean that I sum over linear statistics in these objects here, right? So this thing with the sum is the same. I get this n squared. This was what we had in the normalization, right? And then we get this linear statistics, but we get these products of them. It's sort of a bilinear form in linear statistics here, right? But okay, using these formulas, I can rewrite this expression in this way and insert it into the integral. So then with this normalize partition functions, these capacity terms disappear, and I get this kind of expression. So now I've sort of normalized with the partition function of the interval. This is sort of the interaction I have on the interval, and then we have this extra part. So this is now captures everything about the curve again. Right? Now recall the theorem that I mentioned, this asymptotics of Hankel determinants. It said that if you have this kind of expectation, which is this kind of quotient, which is sort of what we have here also. This is also an expectation, but of this object instead, right? Then if we have this with just a linear statistic, we have this limit with this explicit object quadratic functional a of psi there. Right? Now, of course, we don't have just linear statistic, but just assume, what does this tell you? It says something about converging to a Gaussian, right? So actually, if you just think about what this result tells you for, say, just take one of these linear statistics, it tells you that this converges, I changed the normal, I put a 2 there. This is approximately Gaussian with variance 1. That's sort of what you read off from this Segger type theory, right? And also from the form of this, if I won't go back now, if you go back to this, you see that means also a different K and L here would be independent in the limit. Right? So just assume that. So now we'll be a bit bold here and just sort of hope that things are good. So then I would sort of just replace these objects with normal random variables. Okay? So then we should have the quotients to be an expectation in these normal random variables of this object here. So it's a Gaussian integral. So heuristically, if you believe all of this, then the limit should be, you compute this Gaussian integral. Think of it as a finite dimensional matrix, right? And you compute this Gaussian integral, it would give you this thing here, just standard multidimensional Gaussian integral computation, right? So we could expect this, but this now is a Fredholm determinant instead. This is just heuristics, right? I didn't prove anything, but it indicates something. We somehow should have some proof similar to the way we prove these central limit theorems, the Segger type theorem. So that's actually what you do. You have to go into that type of proof, but that's sort of rather well known how you do these things, right? So you apply the same type of idea to make this rigorous here, which is not easy. I mean, it's quite a long thing to do, but so I won't go into that, but you can sort of expect this answer. So then we have actually a formula now for this limit. So if you believe this argument that I can make it rigorous, then this is the limit we should have. So we have this is minus 1/2 log of the Fredholm determinant with this arc-Grunsky operator. And also, in a sense, as part of the proof, we prove a Segger type limit formula, which generalizes the one we had in the Hankel case. Right? So it's the same structure. We have this psi function now sitting on the curve. I move it with the equilibrium parametrization. This is the parametrization I use. I can move it to have the function psi here. I move it here. And then I expand this in Chebyshev polynomial, just as we did for the Hankel determinant, right? So we have some coefficient there. These were the A case I had previously, right? So then we have exactly the same type of limit theorem here, right? Notice that this form is precisely the same. The only thing, before we had the interval there, now we have the curve. So it's again, you have this function. On this, you extend it boundedly as a harmonic extension, you compute its Dirichlet limit. So this form is actually completely stable, which I think is a bit remarkable here. Right? You can write this in a sort of a Fourier form also, which would then include this arc-Grunsky operator. So we can note this equality between sort of this Dirichlet integral form and this sort of Fourier form here. And actually, if gamma is just the interval, then B is 0 here, and we're back to the formula we had before. So this is a direct generalization of this Hankel type determinant that we saw. Okay, questions?
You chose the Chebyshev basis to make them independent, the Gaussians.
Sorry?
So you chose them to be in the Chebyshev basis because you wanted the Gaussians to be...
Yeah, in a way you could say. I mean, you see that this is the right type of expansion because, as you say, it does appear in this limit theorem. And that, so that is the reason, yes.
How do you make sure that I plus B is a positive matrix? Can you?
Sorry, the
I plus B's matrix is a positive matrices. A positive, definitely positive.
Kosten-Leibowitz.
Huh?
Oh, sorry.
I mean, you need to take the determinant of I plus B.
Yes.
And how do you make sure that the determinant is positive?
Oh, that's a good question. I will answer it in a moment. Yes. No, it's not clear that this makes sense. I didn't tell you any properties of B, right? So and also you need some properties to actually do the proof rigorously. So it's a good point. Yeah. Before coming to that, let me give. Generally it's not easy to compute this, right? There is an example which Widom looked at many years ago in '71, not in terms of Coulomb gases or the perspective I presented here, just as properties of determinants. He proved, from his result, you can read off that if you have a circular arc like this with a certain opening angle, you have this formula. So this is the limit you have of this free energy in this case, in terms of the angle then. If you sit down and write down the equilibrium parameterization, do this expansion in terms of the arc-Grunsky, the arc-Grunsky operator is not so easy. I don't see how to compute that determinant. I mean, it's not an easy thing. So how would I see that it actually equals this? This is not at all obvious if you try it. So somehow we would like to have another formula, right, for this thing. So this is nice. I mean, having a Fredholm determinant is a very nice object, right, in many ways, right? But on the other hand, it could be interesting to see if we can write it in some other form also. Right? So I will come back to your question. But before that, let me go now to the case of a closed curve. Right? So this is something I studied previously. And so in that case, you will see, I will sort of compare this with what I just did. Right? So here we have set up, or recognize we have a closed curve. We have the interior and exterior. We have the conformal map, F and G, from the interior to the interior and exterior to exterior, normalized in the standard way here. Right? So these are sort of given objects here. So what is the equilibrium parameterization in this case? I mean, I just do the same thing. Instead of having the arc, I now parameterize with the circle to the Jordan curve, right? Which parameterization should I choose? Okay, we try the same idea, use the equilibrium parameterization. But this is now, in this case, this is a special feature which didn't really happen here, right? Is that you can use the exterior map to do this, because the exterior map actually maps equilibrium. So in this case, when I parameterize this by the circle, this G maps the equilibrium measure here to the equilibrium measure there. So the equilibrium parameterization just means parameterizing with the exterior map. So then you do the same thing. We have this quotient, right? Now we're using, instead of the interval, we have the circle, right? So the exponentials there, right? So this is the real part of this thing. And this is what you have in the sort of classical Grunsky expansion from theory of univalent functions, is that you expand this in terms of this sort of Grunsky coefficient, and you define this Grunsky operator analogously to what we did.
In the closed curve,
yes.
If you map it on a circle, then equilibrium distribution on a circle is uniform.
Yes.
In the case of the interval, it's not.
No, right.
Just not. But my question is, can you find
here,
the deformation of the interval to some curve where equilibrium distribution is uniform?
Uniform on the curve. I mean, I guess it typically wouldn't be, right? Not on in this.
Circle, half a circle, maybe?
No. I mean, as soon as you have endpoints, it will always pile up at the end. Right? It will sort of it will go sort of diverge at the end, right? So you cannot be, then you would have to have some extra charges and things that we've discussed. You know, you put some extra things, I mean, to make it
So
uniform.
there is no natural figure where distribution will be uniform?
No. So this is sort of the class, that's why we call these arc-Grunsky and so on, because in this case it's called the Grunsky expansion, Grunsky operator. Right? So the analogous theorem in this case, which I proved some years ago and which Paul and Sabradin has also studied, you do the same thing. Now we normalize with you divide away capacity as before, and you take the same object. It converges to this Fredholm determinant now, where B is this Grunsky operator then. You should actually, to compare with what I said, you should actually look at sort of a real version of this, because you're taking actually the real part here. So the natural thing is actually to expand in sines and cosines somehow. And if you think about that, it has this form also where K is now this matrix, which sort of involves a real and imaginary part of the Grunsky. So this is a minor point, but this is sort of the direct analog of what I just had for the arc case. So in this case, when you know things about this, there is a so-called strong Grunsky inequality. So this is for the case of a closed curve, right? So if this gamma is a quasi-circle, then you have this norm of this is actually below 1, right? Bounded by a kappa less than 1, right? And this is true precisely in that case. So this is when you prove this result in sort of the way I described, this is an essential ingredient actually in that proof. So to make what I just described heuristically rigorous, you have to have an analog of that in this case. And this is this bound. Actually, the only thing you need is a bound from below, and this is what we can prove here also. We don't know if there is a bound from the other side in this arc case. But we do prove for sufficiently regular curve. It doesn't have to be analytic, but say C5 or 7, I don't remember now. I mean, so we don't know in what generality. Here it's, it's very weak condition, right? But we don't know the condition here. So this is the answer to it. So this means actually that it is well defined. This is, for sufficient regular class, this is a trace class operator, which is when this Fredholm determinant is well defined. Yeah. But in this case of the closed curve, we do have another expression for this, right? So in terms of this Loewner energy, which we heard about yesterday afternoon, for the curve, we can associate this Loewner energy in terms of these maps, right? I won't say anything about it. We heard a bit yesterday. Yelin has written a very nice short survey about this, which describes different connections. I won't go into this, right? So, but this is sort of a motivation for what I'm saying now, because in this case, so this is all now in the closed case, we do have sort of equalities between these Fredholm determinants and some objects involving, the maps instead somehow. So that you could ask, is there some analogy of this in this arc case also? I mean, can we express this not in terms of the Fredholm determinant, but in terms of sort of maps somehow, right? So this identity here is actually not so easy. It comes from the work of Takhtayan and Theo on the universal Teichmüller space. So, and the proof, it's not just that you look at this proof and see what you do, right? I mean, so this was actually a hard part of this project to try and understand this. So this is the question I'm just said there. So is there a formula for this analogous to this formula somehow, right? Well, it turns out, and this is not an obvious idea, I mean, this has been used by Wisdom in connection with other type of asymptotic questions on arcs and closed curves, is that when you have an arc, you can sort of open up with a conformal map. So you take this map, simple map, this is inverse of this map here, right? If you solve the quadratic equation. But you take sort of the branch cut for this root to be on the curve. Right? So if you apply this map, it will sort of move map the upper part to one part of the closed curve and the lower part to another sort of half of the closed curve. Right? So this maps this arc to a closed curve. We call this the opened up curve. This curve is symmetric. Right? So under the map W maps to W, it sort of maps it into itself, right? Because of this thing here, right? So it's not just any closed curve, right, that you can get. You have a specific symmetry here in this closed curve. And for this, there is an exterior map now from the exterior of this closed curve to the exterior of the unit circle. So that's sort of H, which is sort of G inverse we had before, right? So I mean, in the case of the interval, this is something you may recognize from complex maps, right? If you open up in this way the interval -1 to 1, you just get the unit circle. Right? So this is the sort of the basic example in a way. Right? And then so H is sort of the inverse of the G I had before for this curve, closed curve now. Right? So we define the Coulomb-Loewner energy. Now it's the Loewner energy, which for the closed curve then, half of that, and then there are some endpoints contribution coming from how this H maps these to the unit circle. I mean, they will not necessarily end up, symmetrically or anywhere. They will end up at some points, right? And you compute the derivative at these endpoints. So it's some kind of endpoint contribution here now. But this does give then an expression of this object in terms of sort of these conformal maps, sort of analogous to what we saw for the Loewner energy. So I won't really, the details of the proofs are rather involved, but let me just indicate a few things, right? So is the setting clear? So we have this formula. We want to prove that this Fredholm determinant with this arc-Grunsky is equal to this thing here. So what can you do? Well, typically when you look at things, you vary the curve. So we somehow want to deform the curve, right? So but it's not completely clear how it will sort of move from this curve to that curve in some family, right? You construct this using a holomorphic motion between these, and it should, so then of course these open up curves will also move, and you have to sort of understand some properties of this. But okay, say that we have this family. So then for every alpha, say between 0 and 1, you have this arc-Grunsky for this interpolating curve, right? And we differentiate this. Okay, then classical thing for Fredholm determinants is the derivative of the operator with the parameter, and then you get I plus B inverse here, and the trace of that. So you have to understand that then, right? And now we can recall what I mentioned coming from this Segger type theory, right? We actually had some object involving this inverse. This was this formula for the variance of the linear statistic. Right? It could be expressed as this Dirichlet integral also. Right? So there is what do? You insert the definition here of the Grunsky. It's the only thing we have, right? We have the definition of the Grunsky operator, right? It's Grunsky expansion. You insert it into this, and then you massage this formula and manipulate. You get some kind of Dirichlet integral formula. This does not give you immediately this kind of the derivative of the Loewner energy of this opened up curve. So there is a lot of further manipulations you have to do, but that's the idea. So you can use this type of formula to get sort of integral formulas instead. That's how you sort of can prove this type of identity. But it's not so clear to me why this opening up is a natural operation here. I mean, it's not so easy to see why that works somehow. So in this, if you go back, there was one case where we could compute it, right? And this was when we had this from Widom. In that case, it's very simple. If you open up a circular arc, you actually get a circle. Right? So then we have to, and this H map will map this circle to the unit circle. Right? This is just a linear map. So it's sort of the easiest situation you can have, and you can, of course, compute what this map is. And if you insert this into this kind of formula here, this is actually 0, right? Because we know that the Loewner energy of this opened up curve, which is the circle, is 0, right? So the whole contribution comes from this part here. And then we recover Widdom's formula. So it's sort of a check that this works also. So we didn't call it the arc-Loewner energy, and this is because Yilin here has already introduced another quantity which is called the arc-Loewner energy. So it's already taken, right? So let me tell you what this is actually related also. So what you could do when you have this curve here is to view this as you take sort of the exterior of this curve, right? So this has a hyperbolic structure, right? You can define a geodesic going, sort of completing this curve, right? In C minus this curve, right? And then you simply define the Loewner energy of this arc as the Loewner energy of this closed curve. This is not the same thing as this opening up, right? It's a different construction. Right? So you can see it cannot be just this, right? Because if you did this for the arc, it would be the circle. So this is just 0 in that case, right? Whereas this Coulomb Loewner energy which we had is not 0, so because of these endpoint contributions, right? But actually, they can be related. There is by work of Ellen-Trussell, which we could use. You can relate this sort of Loewner energy of the opened up curve to this arc Loewner energy. Involves some boundary term which comes from the interior map now instead, from D into the interior of this opened up curve, right? Taking a map which fixes the endpoints now. Then you have this relation. So in total, you have that this Coulomb Loewner energy is related to the arc Loewner energy. I have to say this correctly now. Difference is this term here, which is not a very obvious term, right? I mean, it all involves all these maps, right? Anyway, the point of this is that you know from the Loewner energy that it is 0 if and only if this closed curve is a circle. Right? And it's always non-negative also. This is not at all clear from the formulas we had, that this is non-negative. So it's a natural maybe to conjecture that this is always non-negative and also 0 if and only if you have the interval. Right? And this is indeed the case. You can use this formula to prove that. So this is actually greater than equal to this arc-Loewner, which is, we know then from previous results that it's non-negative. And if they are all equal there, you can see that it has to be an interval. Okay, I think this is, I think I'm right on time.
Yeah. Small question. In the closed curve,
yes.
This determinant of Grunsky determinant, right?
Yes.
In large limit become Fredholm determinant. Fredholm determinant of Newman-Poincaré operator.
No, yeah, no, yeah.
But my question is if it's an open arch, is it still determinant of that kind?
It's sort of still, in some sense, the determinant of the Neumann jump operator. Yes, it's somehow the same, but it's
closed curve, not open.
Yeah, because you have sort of a jump over the curve instead of a jump over this. Yes.
But there is a relation between determinant of the Neumann jump operator and Fredholm determinant of a Neumann-Poincaré operator. They're inversed.
Yeah, but we don't know. Maybe I stop and you can take questions afterwards, right? So, okay.